this is R, right? So this is the construction. And let's say if we have this galvanometer set up at this point, right? And this is the battery that we have connected, right? So then if the galvanometer shows zero reading, right? Then the condition of Wheatstone bridge is full. Then what will happen? Then we know that R1 by R2 that is equal to R3 by R. Right? This is the condition of Wheatstone bridge, right?
Yes, sir.
And then in the meter bridge, what is the case? So in meter bridge, you have this 2 point junctions, right? And then you have this meter scale, and this one, let's say this one in here, and then this is connected to some resistance, right? And then this one, this is connected to some resistance, right? This is, I guess, and then you have this jack, you have this battery, and then this is connected, and this here is your jack, right?
Yes,
So
sir.
this is the basic construction of the meter bridge, and this is connected to, let's say, galvanometer, right? So now you connect this device and the length of this wire, right? The length of this wire is 100 centimeter, right? So let's say this is R1, this is R2, and you know the resistance of this thing and you don't know the resistance of this, right?
Yes.
Then what you do is that you have this jack and then you place this jack at this wire, this 100 centimeter wire, right? And at some point, the galvanometer will show zero deflection. So that would be the null point of this resistance, right? You note down the null point. Then let's say the null point reaches at this L, right?
Yes, sir.
So then we know the condition that what would be, so the meter bridge that would be equal to R2 by 100 minus, because this has some resistance and this resistance gets cancelled, right? So then you get this condition that R1 by R2 that is L by
So your screen is stuck.
okay, I got disconnected. This is the structure of the meter bridge. Yeah, is it clear to you, Maria?
Yes.
Yeah, so we have just these one resistance would be known and the other would be unknown, and you have to find out the unknown. So this is the idea of meter bridge. So you have this 1 meter of length. That is why we are calling it meter bridge. Meter means 100 centimeter, right? So you have this meter bridge, and on this bridge you find a null point so that this galvanometer shows a zero deflection. And yeah, so then you can just find out this L point. You just note down this L, And then you know that this would be 100 minus L, and then from this condition you calculate the annual. So this is the working of the meter bridge. And this is based on Wheatstone bridge principle. Clear?
Yes, sir.
Okay, let me shoot. Yes, your voice is very faint. My voice is very,
Sir, can you hear me now?
it's still very, right.
1 second, sir. Sir,
Now
can you
it
hear
is.
me now?
Yes, yes. Now, sir. Yes,
Sir,
Anu. Yes.
so we did this experiment in school also, and now that I'm looking at the observation table, the R1 is like 200, 230, 250. But how is that, sir?
30 ohm, that is totally possible, right? 230 ohm, that is totally possible, right? So, but yeah, generally the resistance that they give is they generally gave this right. Uh, I don't know. You can calculate the resistance of that thing because you know that the colors patches, right? Those are the things that they generally right. So what are those things for? Because you have four lines, right? One is the gold one that shows the power of the resistance, and then you have three stripes, three different colors stripes. Yeah.
Yes, sir. But like R1, isn't R1 like the resistance box where we have to remove like the keys from it?
Yeah. Okay. So there would be the boxes. Yeah. So we have these resistance boxes, right? So those are resistance box, right? And these are pins that you plug in, right? So these are the pins that you plug in. So those pins are, I guess, 2 ohm, 5 ohm, and yeah, those are the
Yes,
pins.
sir. 1 ohm and all that.
Yeah, 1 ohm. Yeah. So yeah, you just plug in those pins, and let's say that you put, let's say, 5 or 50, right? And generally, you get the balancing point. Let's say that at 30 centimeter, you get the balancing point. So this would be 30 divided by 100 minus 30 is 70, and then let's say this is 6. So yeah, you are saying 6 3 is 18, so this should be in let's say 2 ohm.
18 ohm.
Yeah, so these would be the values. If you have these, maybe those are in kilo ohms, right? Maybe those are in kilo, ohm, but
Mm,
generally the box is 500 resistance, right? Or maybe Aisha could, yes, Aisha, do you have this experiment meter bridge in your school?
Yes.
And did you perform that experiment? How did you perform that? What was the resistance of these resistances boxes? Yes. And
So we
maybe
did it, but then I was absent that day.
you were absent in that class.
Yes.
You did not do this practical.
I wasn't.
So you don't have that practical notes. Right. So maybe you can check, Mariam, the values in the let's say we just check it in the Google, right? That we have that practical. So just write meter. Yeah. What? So we have already.
Sir,
Yes.
sir, the unknown resistance that we got, like the R2 that we're getting, it's like coming in like 371.718 ohm.
Yeah. So 300 ohm.
71, yes, 0.78. 718.
100, 300. That is quite a lot, right? Yeah, so generally the value that you get is how much everything. There are several nodes. There are several images that I see, right? Yeah, this is very good. Yeah, go to the Google browser, right? And we have this knowledge universe online. So in there, yeah, showing this, right? So,
So can you repeat the website?
yeah, go to knowledge universe online, right? And okay, or you can write. You write. You write that meter bridge experiment class 12 practical. I can, yeah, let me just write it down here and I will share it there. Right. Let me, Aisha, please wait a moment. We'll start quickly, but, and this is a very simple experiment, right? So let me just give, and they have all those readings as well, right? They have those readings and you can look at those. And yeah, you will not get, values as you are getting 200 ohm you are getting. Maybe the resistance box that you are using, they have quite a lot of quite high resistance, right? Maybe they have okay, one moment, wait, yeah, this very good. Yeah. Okay, yeah, check this link. And yeah, why they are writing? So the unknown resistance that they are writing, that would be like you have to calculate the unknown resistance. Like this would be 100 minus L. So this is the unknown resistance, right? So unknown resistance would be how much? That would be because they are putting the unknown resistance in here, right? So this is they are saying X. So what would be X then? If you put your unknown resistance in here, so this would be the formula. If you put your unknown resistance in here, so you have to find R2, right? So R2 would be how much? R2 would be, this will go in there, right? Minus L divided by, uh, right, divided by L into R. this would be if we are joining the unknown resistance in here. The idea would be this, right? Meter bridge idea. Same idea. And if we have put, because in the, did you go through that? Yeah, that would be also helpful to you, Aisha, right? So did you guys go through that link? Did you open that link, guys? Yes, Mariam, did you open that?
Yes, sir.
And look at the diagram, right? So that is, yeah. So the unknown resistance is attached in the right hand side, right? So that is R2. And then they have made the table, right? So then R2 would be 100 minus L by L into L, right? So did you check that table? And in here they are getting,
Yes, sir.
yeah, in here they are getting 1.3, right? So this is how things. Is it clear? You
Yes,
know,
sir.
good. So yeah, generally you will get the value around from this experiment. You will get the value around 1, 1.5 or 1.6. That, but that depends upon the null point, right? I guess if they give you some different resistances, then yeah, it's totally fine, right? That is totally dependent upon. Maybe they are giving you the resistance, the unknown resistance whose value is pretty much high, right? So, yeah, then you would be getting that much, right? So don't think that you are getting so much high, right? And is it happening for the other people as well? Did you check with the other practical notes? Did you check with the other people? This would be very easy, right? We have to just move this jack. So this is called jack, and we have to find the null point. Note down this length. Note down this. We know already the known resistance. Then we do it multiple times, and then we take the evidence. So that is how we do. And generally, the unknown resistance is attached in the right hand side. So then you will get this formula. Right? So, yeah, is it clear, Maya? Any other doubt that you have?
Yes, sir.
Yeah.
No, sir.
Yeah, all the best for your preparations, guys, right? And revise all the chapters. Right? And yeah, in the last class, okay, so Arsalan is still not here, right? It's not still. Because, yeah, this chapter would be over, right? In a few moments, and then we will go to the atoms nuclei chapter. Nuclei chapter is also very short. In nuclei chapter, we have this size of the nucleus, binding energy, and nuclear reactions. Three topics. Then that chapter is. That is a very small chapter. Okay, so in the last class, we were talking about, right? We were talking about this Lyman series. And what was this Lyman series? If the electrons were jumping from, let's say, 2, 3, 4, 5, 6, from that, those energy levels to the first energy, right? Ground energy. So that series is called the Lyman series. And this series lies in the range of, so they emit the radiation in UV range, ultraviolet range, right? And you guys have already studied about that electromagnetic spectrum, right? Ultraviolet is how much? How much would be? Because we know that 400 to 600, that is, or maybe 400 to 700, that is visible range, right? We know that 400 to So we know that 400 to 700, that is visible range. And which wavelength is this? 400 nanometer. Which wavelength is this? For which color of line? For which color of line? Yes. Yes, Aisha, what did you say? For which color this is the wavelength? Violet, right? Because violet has the smallest wavelength in visible range, right? Violet has smallest wavelength, highest frequency in the visible range. So this is violet, this is red. So ultraviolet would be in this somewhere around. So less than 400. Infrared, then infrared comes here. So that is more than 700, right? These are the electromagnetic spectrum you guys have to remember, right? That is very crucial. We have this infrared, and then we have these radio waves, right? Microwaves and radio waves. So these are here. And then we have these X-rays and gamma rays, right? These lies in that. You guys have to remember all these electromagnetic spectrum. These are very important. Okay, so now let us come to this other series, which is why this is. So the other series that is there, the emission spectra, and that is Balmer series. Pani, okay, so Balmer series. What is Balmer series? When the electron, let's say this is the first energy level, right? And then we have this second energy level. And then we have this third, fourth, fifth, and this infinite. These are actually getting shorter, right? So this is third, fourth, fifth, sixth, and so on. So if the electron is jumping from 3 to 4 to 2 and 5 to 2 and all these things. So then this is called the Balmer series. For Balmer series, the wavelength is what? This is represented by RH and 1 by this value we know already. This is how much? N1 is how much? The Balmer series N1 is 2 and N2 is N, right? Which is greater than, right? So which is greater than where N is 3 and so on. So this is 2 minus 1 by N square, right? And then this lies in the, so this lies in the visible range. Right, and then you guys can also calculate the maximum wavelength, right? So this would be maximum length, the wavelength would be how much? That would be for the lesser energy level, right? So maximum delta E is Hc by lambda, right? And if this is very high, then this is very low. So if this is low, then this would be high. So for n equals to 3, that would be maximum width. Right, this is 2 square. So this would be, you calculate what would be lambda max, and then similarly lambda minimum would be there. So for lambda minimum, you have n, which is infinite, right? So these are, and these lies in the visible. So this is about Balmer series, and then you have Paschen. Right. So I will write directly that for Paschen N1 is 3 and N2 is N, where N goes from 4, 5, 6, and so. And this also lies in the what? So this is what 1 by lambda. That would be RH 1 by 3 square minus 1 by n square. So this is the Paschen series, and then we have a bracket, and this also. So this lies in the infrared and this is the bracket. So bracket for n1 equals to 4, n2 is n, where n goes from 5, 6, 7. So and then 1 by lambda, that would be how much? RH 1 by 4 square minus 1 by n square. And again, this lies in infrared. Okay. And then lastly, you have this Fund series. What is this Fund series? N1 is 5 and N2 is N, where N goes from 6, 7, and in here, what would be 1 by lambda RH 1 by 5 square minus 1 by n square. And this also lies in the infrared, right? So if somebody asks you that Lyman beta line has, yeah, what would be the wavelength of Lyman beta line? So you guys can calculate N2 is 3 and 1 is 1. So these are very important things, right? Lyman alpha, Lyman beta, Lyman gamma. These are important spectrum, and all these ones we can. So if you please, you guys note it down, and then we will make a diagram and this chapter is. Please note it down, and if you guys have any doubts, please let right. Yeah, whenever you have, you guys have completed noting it down, please. Yes, Aisha, are you a practical student?
No, sir.
No. Okay, yeah. So also please prepare. Uh, we just go through right practical. So your practical files have been checked, right?
Yes.
Yeah. And I guess they give 10 marks for that. In our days, they used to give 10 marks for practical. 10 marks for practical notebooks and 10 marks for all those Viva and 20 marks for that experience. Yes, whenever you guys have noted it down, please tell. Done. What about you? I am done.
No, it's not yet.
Yeah, Aisha has did. What about you, Maria? 10.
My name is not here.
Yeah, Aisha, are you saying something? Your voice is mixed up. So other noise are there. Oh, Mariam is not here. Oh, what happened to Mariam? Oh, she got disconnected. She got disconnected. Okay. Maybe her practical exam is tomorrow. Maybe, yeah, yeah. Let us let us understand. Let us draw all these things in one diagram. Right? So let us draw all that information in one diagram. So how can we draw that? Why this is not being done? Say we have this one. Okay, let me draw that. It will take forever. Let me draw this. So the other one is this. This would be very ugly looking, but what I can do, right? I want try to draw that figure, but yeah, it was taking a lot of time. So you make those very beautiful circles, but I cannot draw because it is taking very a lot of time. I would draw it like this. This is not a circle, but how many we have drawn? One, two, three, four, five, six, seven. Let us draw one. It, right. So this is n equal to 1. This is 2. This is 3. This is 4, 5, 6, 7, and 8. And let us draw one. And this is 9. So first, let us draw the Lyman series. So this one is the Lyman series. Right? This one, this one, this one. So this is the Lyman series. And this wavelength right? Because energy is minimum, so this wavelength will be maximum, and this is right. Similarly, this is the Lyman and then we have this Gaussian Balmer series. So in Balmer series, it is going to this one. Okay, I did not draw the third to two, and then four to two, then five to two, then this one, this one, this. Oh, I have made this in times. Yeah, so this would be lambda maximum, and this is lambda minimum, and this is Balmer series. And then what do we have? So this is second one, and then we have this third. Third one is this one. So again, this is lambda maximum. This is lambda minimum, and this is Lyman Palmer Gaussian. And then we have a bracket, right? So this one is right. This is again lambda maximum. This is lambda. Oh, this is not the. For this case, this is lambda, right? Because lambda minimum would be at infinity. But we are just taking this case, right? Because lambda minimum for this diagram only, this is lambda minimum. And then we have this is bracket, right? Lyman, Balmer, Paschen, and Balmer, Paschen bracket, and different one. This is going from 5. This one would be maximum. This one is minimum, and that is this is the diagram, right? And this explains all these things. So that goes from n to equal to 5, and this goes from 4, this to 3, this to 2, and this to 1, right? So all these are stages. Okay, and this diagram contains all the transitions. These are different transitions. You please note it down. Is this clear to you, Aisha? Is it clear?
Yes.
Yeah, please note it down. And then we will talk about, so this chapter would be over and then start. Yeah, yeah. Yeah, whenever you have noted down this diagram, this is horrible looking diagram because I wanted to draw a full circle, but yeah, I was not able to do it. But yeah, these being circular. We have this one more. One more is this. Done. Okay, so now we have understood all the aspects of those atomic structure. Now let us try to understand. Right, and I will write this part. Right. Why this is pretty. Right. Okay, so before we talk about nuclei, let us talk about certain units. Certain units in which we will measure these all these nucleus particles and all those elementary particles. Right. So before we do that, right, we already know that the size of the atom is angstrom, right? And we also know that, right, we also know that, so we know that atom size is how much? This is angstrom, right? And the nucleus is inside the atom, right? So its size will also be very smaller. So the size range or the range of size of nuclei is how much? That is in Fermi, in FM, where this is Fermi, where 1 FM is 10 to the power minus 15 meters. So this would be, right, so this is 5 times smaller than this atomic size. Right, so atomic size is how much? That is 10 to the power minus 10 meter. But this nucleus size, that is 10 to the power minus 15 meters. So that is pretty smaller than this 10 to the power minus 10 meter, right? And in nucleus, what are the constituent particles of the nucleus? What are the constituent particles of nucleus? Let's say this is a nucleus, right? So the constituent particles of nucleus would be proton, right? And neutrons, right? So there would be protons and there would be neutrons. And the size is how much? Size is 40. And if you can tell me that these protons and these protons, how can they be together? Can they be together? What would be the force between the proton and proton? What would be the force? Yes. What would be the force between proton and proton? Proton is what is the charge of proton? Yeah, your voice is not audible. Positive, right? So proton is positive and the other proton that is also positive. So they will repel each other, right? But the nucleus exists, right? So how this Coulomb force is not there in the case of this nucleus, right? So we know that these Coulomb forces are there. So P and P will have Coulomb force. But to attract these things together, right? To hold these things together, to hold the nucleus together. There is another force, another force which is called nuclear force, right? So nuclear force would be there, and then you can ask me that why this nuclear force is not around when we have two protons that are right. So why we don't have these nuclear force when these protons are at some distance? They are not inside the nucleus. If they are not inside the nucleus, then why these protons? Because these nuclear force acts between neutron and proton. This acts between neutron and neutron. This acts between proton and proton. So all these three will have nuclear force, right? All these three will have nuclear force. But let's say if you are not inside the nucleus, then why this nuclear force is not there between the proton and proton? Yes. Can you tell me? Can you identify the reason? Can you identify the reason, Aisha? What could be the reason that if these protons are not inside the nucleus, they don't experience this nuclear force?
So
Yeah.
because they're giving uh,
Yes.
force,
It's what?
they're providing the force that holds the electrons.
Yeah. So the force, the force that is holding the electron is binding force, right? So nuclear force of attraction between the electrons and the nucleus. That is Coulomb force that is holding that. But I'm asking that if these protons they are not inside the nucleus, right? Let's say if you have a proton here and if you have a proton here, so they will not experience nuclear force. Why? Because this nuclear force is a short range force, right? The range of this nuclear force. So the reason is that nuclear force is a short range force, right? So this acts only we have the distance is femtometer Fermi. So whenever they are apart from 1 Fermi, right? Then this nuclear force will not act. So because outside the nucleus, the separation is not that close that this force can hold. So that is why outside the nucleus you don't have this nuclear force. Then what force dominates? Can you tell what force dominates? What force dominates? Can you tell me, Aisha? Think about it. We have only four kinds of forces. We have gravitational force, we have weak force, right? We have this electromagnetic force, and we have this nuclear force. Only four forces are there in physics. Only four forces, right? Nuclear force, gravitational force, electromagnetic force, and weak van der Waal force, right?
Gravitational.
Yeah. So if they are not inside the nucleus, then Coulomb force, electromagnetic force, that will dominate, right? Proton and proton, they are positive charge particles. Proton and proton will repel each other. Why? Because they are not inside the nucleus. So if they are not inside the nucleus, then this force would not be there. So then Coulomb force will dominate. What? Inside the nucleus, right? Inside the nucleus, have you have Coulomb force. Coulomb force is dominated by nuclear force, right? Although these protons and protons, they are repelling each other, but the holding capacity of nuclear force is so strong that it overcomes this Coulomb force. So that is why inside this nucleus, these protons and protons are together, right? So that is why dominated by nuclear force. That is why inside these nucleus, you have these protons together. Otherwise, you cannot hold two protons together, right? So that is why these nuclear forces are very important. And inside this nucleus, so nucleus is made up of two particles, right? And one is neutron, and the other one is proton. And together they are called nucleons. Right, so these are the things about this nucleus, right? So nucleus is stable by this nuclear force, right? And inside the nucleus, the Coulomb forces are comparatively very small, and nuclear force is very large. That is why the Coulomb force is not dominating inside this nucleus, and that is why all these protons and neutrons are together. And all these neutrons, proton and proton, they are acted by this nuclear force. And this nuclear force is a short range force, right? Whenever the separation exceeds some value, let's say femtometer, then this nuclear force will not be there. So this nuclear force will vanish whenever you exceed this. These are particular things about this nucleus. And then the energy that the unit of energy that we would be talking about is mega. So energy of right. So we know that what is the size unit that we will be taking? Unit of energy in this chapter would be mega electron volt. So how much is mega electron volt? Mega is 10 to the power 6 electron. And you already know that 1 electron volt is how much? That is 1.6 into 10 to the power minus 19 joules. So these would be the units that we have to be very careful. Right, we will write all the units in mega electron volt. And then very important. So this thing is very important. Always, so unit of size would be femtometer, right? Unit of size would be femtometer for me, and unit of energy would be mega electron volt, and the mass, right? The unit of mass, unit of can you go to the market and ask for 2 kg of electrons or 2 kg of protons? Can you do that? Right.
Yes.
Obviously not, right? Because the mass of the electron, protons, and neutrons are so small that you cannot measure them by this kilo scale, right? So that is why you require another scale which is very small. And in that scale, you can measure the mass accordingly, right? So that scale is called atomic mass unit or 1U, right? And how much is this thing? This is the mass of the mass of or 1 by 12 of the mass of C12 atom, carbon 12 isotope atom. So, and when you calculate this mass, this is found to be 1.66 into 10 to the power minus 27 actually. So this is 1 U. And with this 1 U, we will measure all the masses. So mass of the proton, that is how much? That is 1.67 into 10 to the power minus 27 kg. But in here, we will measure it in 1U, which is 1.0073. Right, so this is the mass of the proton that we will be taking in atomic mass unit, and mass of neutron, that is also 1.674 and into 10 to the power minus 27 kg. And this is 1.0086 U. And then we have mass of electron, which is 9.1 into 10 to the power minus 31 kg. So this is 0.00055. So this is the mass of the electron and mass of hydrogen. Hydrogen is made up of what? What is the constituent units of hydrogen? What is hydrogen made up of? Hydrogen has this proton inside the nucleus and then this one electron. Right? So it has one electron and one proton. That is the hydrogen, right, Aisha? Mass of hydrogen, that would be mass of electron plus mass of proton. This is how much? 1.0073 plus 0.0005. Right. So how much is this thing? So this is 1.0078. This would be the mass of hydrogen. So we will measure all the mass in U, atomic mass unit. And these are very important numbers. Please remember, right? These are very important for this chapter. Okay, so please note down this thing, and then we will talk about. Right, then we'll talk about the other. Whenever you want me to scroll it down, please tell.
Um,
Yeah. Okay, then please note these things down. Yeah. Okay, so now let us understand about this very important relation. So the size of the right. Before we do that, so we write right. How do we write? How do we represent representation of the element? Right. So let's say we have this X element. So this element is represented by its this mass number and this atomic number, right? So Z is number of protons, right? And this is called the atomic number. And then we have this A, which is mass number, right? And this is this is what? This is number of neutrons. So this is neutron plus protons, right? So if we want to calculate the number of neutrons, so number of neutrons is what? That is A minus of Z. This is the number of neutrons, and yeah, these are. So then we have three kinds of properties. One is isobar, right? So what are the isobar? And we have isotopes, and we have this isotopes, right? So we have these three kinds of things. So for isotopes, the atomic number is same, the mass number is different. And for isobar, the atomic number is different, but mass number is same. And for isotopes, the neutron number is right. So these three kinds of element are there, right? And then we talk about, and then we talk about this size of. So the size of the nucleus is represented by R, and it is proportional to the mass number, but 1 by third power. And if we remove the proportionalities, this goes as R naught A 1 by T. Right. This is how the size of the nucleus varies. So if we have different mass numbers, then the size of the nucleus would be different. And this R naught value is how much? That is 1.2 Fermi, right? Which is 1.2 into 10 to the power minus 15 Fermi. This is the value of R, right? And similarly, we can calculate the density of the nucleus. right? So density of the and how this density of nucleus varies. So this is mass by volume, right? So mass of the nucleus would be how much? What would be the mass of the nucleus? Yes. What would be the mass of the nucleus?
1.695.
Yeah, so mass of the nucleus, let's say you have the mass number A, and then you have this mass of the neutron, right? So then this would give you the total mass of the nucleus, right? So you have n number of neutrons, whatever number of neutrons are there, and then you multiply it by this mass of the one neutron. So that would give you the mass of the nucleus, right? And then you divide it by the volume. So the volume would be 4 by 3 pi r cube. And if you write this thing down, right? So this would be how much? This is A, and this is Mn, right? And then this is how much? 4 by 3 pi. This is R naught and A 1 by 3 cube. This would be how much? This would be A and Mn and divided by 4 by 3 pi and R naught cube and A 1 by 3 and power 3. So this 3 and this 3 will cancel and this would be A mass of the neutron or this is the mass of let's say one nucleus, right? Then this would be how much? 4 by 3 pi R naught cube and this is A. So this A and this A will cancel and then what would be this thing, right? So this would be M and let's say mass of the nucleus and divided by 4 by 3 pi r naught. And so this would be the density of the nucleus. And you can see that this density, so this mass of the nucleus is constant and this R naught is a constant. So density would be constant value, right? So density of all the elements remains the same, but the radius of all the elements or nuclei, uh, the nucleus of different elements, they changes, but nucleus density of the nucleus of different elements, they don't change. So that is why all the nucleus of the all the density of the nucleus they are same. This is the other property. Please note it down and yeah, please talk. If you have any doubt, please ask. Please note down. Joined. Yeah, please note down this one. And if you have any questions, please add. So this R, I should write that this R is radius of the nucleus and A is mass, right? Yeah, whenever you want me to scroll down, please. Whenever you want me to scroll it down, please.
Energy.
Yeah. Okay. So please note down this part, right? And this here, right? This is A is again mass number, and this is the mass of the neutron, right? So then the mass of the nucleus would be how much? So you have, let's say, A is the number of protons plus the number of neutrons, right? And if you multiply them, we have approximated them because you see that the mass of the neutron and proton are nearly same, 1.67, right? So let's say we know that what is the total number of proton and neutron, right? Let's say we have three proton and two neutrons, and then we multiply it with the mass of the neutron, then we will get the mass of the nucleus, right? So that is how we calculate the mass of the nucleus. And yeah, we have approximated it with the neutron because the mass of the neutron and mass of the proton, they are near, right? So that is how we calculate the total mass of the total mass of nucleus. That would be how much? That would be total number of neutron and proton into mass of one neutron or proton, right? Because both have the same mass, so then we can right. Then this would be how much? So this would be A, and then so that is how we have approximated. Right. And we see that the density of the nucleus of different elements, that will always be same. So every element has the same density of the nucleus, but they have different size of the nucleus, right? Different size, the nucleus have different size, but the density remains the same. Yeah, whenever you have noted it down, please. Whenever you have noted, please.
Done.
Done. Okay, so I guess all the people are not here, so we'll stop here, right? And in the next class, only two topics we have to cover: binding energy and this uh, nuclear reactions. This chapter will be over, and this semiconductor is theoretical chapters. We have to learn a lot of theories. Yeah, we'll talk about that, and then I will quickly